All right. So this is sort of embarrassing, and I don't like to do this. But what we're going to do, rolling without slipping, it's simple, it's important, and so you need to just scratch out all the rolling without slipping stuff we did last time, and I'm going to do it better today. Okay? So what? So there was stuff, it wasn't the whole class last time. There was some stuff we did before that, but just get rid of this stuff on rolling without slipping, and I think you'll find that it makes a lot more sense this time. Okay, so rolling without slipping, it's a useful idea. It comes up a lot, and it's a nice way to think about combining circular motion with relative motion. So those are kind of the two reasons that I like it. So it's a good combination of circular motion and relative motion. And we're going to make the following assumptions. The first one is at the contact point with the ground, the velocity of that point is equal to 0. That's a requirement. If the velocity of the point touching the ground wasn't the same as the velocity of the ground at that point, then it would be slipping. So at the contact, the point on the wheel has 0 velocity. The second assumption, and it's similar, is so we can't say that at the contact point the acceleration of that part of the wheel is equal to 0, because there's always going to be some centripetal acceleration. But what we know is that the part of the acceleration that's parallel to the ground has to be equal to 0 for that contact point. So at the contact, the point on the wheel has 0, I'll call it A parallel. So that's the part of the acceleration vector that's parallel to the ground, parallel to the surface. And then the last assumption we're going to make is that at the center of the wheel, you have 0 A perpendicular, and what I mean by A perpendicular is the part of the acceleration vector perpendicular to the ground. Okay, so that's just saying that the center of the wheel isn't bouncing up and down. It's moving along parallel to the ground. And I'm going to do this. I think these are the same numbers I used last time. So I'm going to demonstrate a calculation of the velocity of the center and acceleration of the center of the wheel given an angular velocity vector and an angular acceleration vector. Okay, so first let's do the velocity. And let's say that here's what we have. So we have a wheel rolling along the ground. I'll call this point the center and this point B for the bottom. And it's moving this way, which means that its angular velocity has to be this way. And that's 2 radians per second for this example. And the angular acceleration is 10 radians per second squared in the same direction. So since the angular velocity and angular acceleration are in the same direction, in this example, the wheel's speeding up. Okay, so first we'll do the velocity. So think of this as a relative motion problem. The velocity vector of the point B relative to the ground is equal to the velocity vector of the point B relative to the center of the wheel plus the velocity vector of the center of the wheel relative to the ground. And with all circular motion problems where you're combining circular motion with relative motion, the part where you're calculating, so the calculations relative to the center are where you use those circular motion calculations. Okay, so any calculation relative to the center, you're treating it like the center is fixed and you're just calculating circular, quantities about the center. Okay, so what do we know? We know that the velocity of B relative to the ground is equal to 0. We know that the velocity of B relative to the center is equal to omega cross r. And the r that we're going to use in this case is from the center of the circular motion to the bottom of the circle in this case, because we're trying to calculate the velocity of the bottom, assuming that that center is fixed. And so our omega is 0, 0, negative 2. And it's negative because it's clockwise, yeah, or if you're thinking about it in 3 dimensions, it's negative because the positive z-axis goes this way, our rotation is this way, which puts the axis direction in the negative z direction. And then we'll cross that with the r vector. I didn't give the radius, but so let's say the radius of this circle is 0.1 meters. Okay, so that r vector is 0, negative 0.10. And so the velocity vector is negative 0.2 meters per second, 0, 0. The wheel's moving in the positive x direction. I'm using just a standard coordinate system like this. So does it make sense that we got a velocity here of in the negative x direction? It does make sense because what we're doing for the velocity of b relative to the center is we're assuming that the center is fixed, and we're calculating the velocity of that point on the bottom. And at the bottom, the velocity is that way, okay, if the center is fixed. All right, so now we can put it all into the relative motion equation. So we get 0, 0, 0. That's the velocity of b relative to the ground is equal to the velocity of b relative to c, so negative 0.200, plus the velocity vector of c relative to the ground. That's what we want to calculate. And so rearrange these, and you get the velocity of c relative to the ground is equal to 0, 0, 0 minus negative 0.200. And so you get a velocity of the center that's equal to positive 0.2 meters per second, 0, 0. Yep.
So are you rolling without slipping from it'll just be happening rolling then?
It will be, if it's rolling along an incline and your coordinate system is not oriented with the incline, you know what I mean, then not necessarily. It'll always be parallel to the surface, but you could have x and y components. But if the ground is horizontal, then it'll always be in the x direction. If it's vertical, rolling up or down, then it'll just be in the y direction. But what would change that is your r vector. If it's rolling like this, your r vector isn't in the negative y direction anymore. It has an x and a y component. Okay, so now the acceleration. We're going to make two assumptions here. They're the last two ones that were listed at the start of this. The first one is that at the contact, the parallel part of the acceleration is equal to 0. And the second one is that at the center, the perpendicular part of the acceleration is equal to 0. Or, in other words, in calculating the acceleration of the center relative to the ground, we can ignore any terms that are perpendicular to the surface. Okay, so our relative motion equation says the acceleration of b relative to the ground is equal to the acceleration of b relative to the center plus the acceleration of the center relative to the ground. And again, this is the one, since this is a calculation of motion of something on the circle relative to the center, this is the one where we're going to use circular motion equations. Okay, since we're trying to find the acceleration of the center relative to the ground, anytime we have a term in our calculations that's perpendicular to the surface, we're going to ignore it. Okay. So we're ignoring any terms perpendicular to the surface. Okay, so first let's think about the acceleration of B relative to the ground. We can break this up into a part of the acceleration that's parallel to the ground plus a part of the acceleration that's perpendicular to the ground. This one is equal to 0 because of the assumption of rolling without slipping. And this one, since it's perpendicular to the surface, we're going to ignore that. Okay, so this is equal to 0 for this calculation. Then the acceleration of the acceleration of the bottom relative to the center. This is where we use our circular motion calculation. That's equal to alpha cross r plus omega cross quantity omega cross r. And we have to think about the directions of these terms. This is the tangential acceleration. And this is the centripetal acceleration. And we're talking about, there's our circle. We're looking at the motion of this point relative to the center. And so the tangential acceleration is this way. The centripetal acceleration is this way. And so we're going to ignore the centripetal acceleration because it's perpendicular to the surface. The angular acceleration is 0, 0, negative 10. The r vector is 0, negative 0.1, 0. And so the tangential acceleration is negative 1, 0, 0. And so go to the relative motion equation. We have that the acceleration of the bottom relative to the ground is equal to the acceleration of the bottom relative to the center plus the acceleration of the center relative to the ground. And we're only thinking about these components that are parallel to the surface. So we have 0, 0, 0 is equal to negative 1, 0, 0 plus the acceleration of c relative to the ground. So the acceleration of c relative to the ground is equal to 0, 0, 0 minus negative 1, 0, 0. So you get 1 meter per second squared, 0, 0. velocity. Okay. Any questions about that calculation? So I'll give you a couple of assignment questions where you have to do problems like that. So let me do one more circular motion, relative motion thing. So biking in the winter, my hands stay toasty. But my feet get cold. WTF. Okay, so it has to do with wind speed. So it's a wind chill thing. Due to the extra speed of your feet relative to the ground at some points during the pedal stroke. So let's see how that works. So here's the bike. My bike doesn't really look like this. And let's say it's going this way at 7 meters per second, 15 miles an hour or whatever. And my feet are going around in a circle like this. If this is traveling this way, my feet are going around this way, and we're going to calculate the velocity of this point, well, F for foot. And I'm going to make the assumption that the radius of each foot's circular path is 0.2 meters. That's about right. And the angular velocity is 10 radians per second. With respect to. Okay, so what's the velocity of the foot at the top of the pedaling motion relative to the ground? Actually, you do this. Okay, so we're going to do velocity of the foot relative to the ground is equal to velocity of the foot relative to the center of the crank plus, this thing is called a crank, I'm not talking about myself, and velocity of the center relative to the ground. And this is the one that's circular motion. Okay, so, and I guess this one, notice that what's the velocity of the center of the crank? Right, the center of that crank is moving along with the rest of the bike, so this is 7 meters per second this direction. So velocity of foot relative to the center is equal to omega cross r. Omega is, that's in the negative z direction, so 0, 0, negative 10, crossed with the r vector from the center of the circle to F is 0, positive 0.2, 0. And so you get 2, 0, 0. The velocity of the center relative to the ground is 7, 0, 0. And so the velocity of the foot relative to the ground is equal to 2, 0, 0 plus 7, 0, 0 equals 9 meters per second, 0, 0. Okay. So your foot's moving faster than your hands. Any questions about that? Well, the next topic that we're going to go into is, so we're done talking about kinematics, so now we're going to talk about kinetics, and so I guess on Monday I'll start talking about free body diagrams, and we'll start going into Newton's laws for particle kinetics. But let's stop for today, and you can just take this quiz.